Hi, everybody. First of all, thank you for showing up. I really appreciate everybody making the time for this. This is part one of a series of three Apache Flink presentations that I'm writing. Um, I might be doing this 2 weeks apart rather than a month apart because um, simply because I haven't done LA Jug in a long time, and I don't want to waste my own time. Like I have them already, and I don't want to wait that long. I think it'll help me out in my career if I flush these out faster. So that's why I would rather do it in 2 week intervals. So I'll probably post it after this meeting on Meetup, but I will have another presentation ready, and that's on some of the patterns that I recognize when working with Apache Flink. From the get-go, I want to state that this meeting is more for people that are just getting to learn Apache Flink. It's not for people who have worked with it a long time. A lot of this information might be redundant. At the same time, some of my perspectives on this might help you out rather than going to all the documentation, because I will talk about a few of the things that I struggled with to learn, which I think will be valuable to you. And you might have the same perspective as that I do. Um, so let's begin. I'm going to the slides. My name is Marco Villalobos. I'm open to work at this moment in time, which is April 3rd, 2024. I've been a software engineer and a software architect, and one thing that I really enjoy doing is working with Apache Flink and doing stream programming. I have a lot of fun with it. Um, I, I've I've worked on other distributed systems before and microservices before, and this is more entertaining for me than the other type of work, but who knows what comes next. I took that picture today, by the way. All right. Uh, so I'm going to introduce Apache Flink. At a minimal, Apache Flink will read data from some source, go through one or more operators, and save it in some sync. The typical source that uh, that you will find in Apache Flink applications are Apache Kafka or Amazon Kinesis. And, needless to say, it's a low latency stream programming application platform. Um, from an architect's perspective, I like to think of it as like a horizontally scalable distributed trigger that that applies business logic upon a stream of data entering a system. Or you could also think of it as a point cut, an AOP. Um, your data source is Apache Kafka, for example, and you're reading data from it, and you want to apply this trigger to the data, and you could save it in some other data store or do something more complex than that. So from a bird's eye point of view, that's kind of how I view it. Um, so if you're doing like a large scale system design, well, quite often something like Link would just be a small part of it. And you would think of it as like a trigger for the data. So you could apply some business logic to it. Before we get deeper, though, I will give you some historical context of the evolution of these data processing frameworks. Traditionally, and I'm talking about like 20 years ago, we had data warehouses where they would get data from with an ETL process from many different transactional databases, and then store it into some massive data warehouse, which was usually vertically scaled. And it worked for that scale of data back then, but if you had to do that today, it would be very expensive using the traditional method. Um, and the data warehouse, they would generate reports and run these ad hoc queries, and um, let me move that. Let me move this too. Sorry, some of the prompts in Zoom are in my way when I'm reading the slides. How to move them right now. Oops. Ah, okay. And then around, I would say around 2007, the late first decade of the 2000s, MapReduce became a very popular distributed processing framework. Um, and in that scenario, it was batch processing, but it was distributed, used commodity hardware, and the scale of data was so large that they would ship the code to the data rather than running the data through the code. And it worked, but it was slow. Um, but at least it worked. Like the other systems back here in the traditional data warehouses, you couldn't even scale it out really. It was very expensive to scale out. But this one was designed to scale out horizontally from the beginning. And there was a lot of hype behind it when it first came out in the latter part of 3 decades ago, the 2010s, I'll say. Um, and the programmers that worked in that field, they were very rare, a rare special breed. Um, Now we have stream processing. Um, and stream processing, what it does is it processes the data as you're ingesting it. Uh, if you like to think of water as an analogy, you would say the source of the data is some spring and it's flowing and you do something to that stream before it enters the lake. Uh, and if you compare this to Hadoop, for example, Hadoop would do batch processing upon the data within the lake, but stream processing does computations on the data as it's flowing into the lake. I like to keep that analogy when I try to teach people what stream processing is. Oh, one more thing. Always feel free to interrupt me and ask me questions. I'll gladly answer them along the way. I don't mind that at all. Um, all right, so let's get down into some of the fundamentals of Apache Flink. Um, so if you decide to use Apache Flink, one of the important things to know is what use cases you're gonna be supporting with it. Like, you don't want to use it for any reason. There's special use cases where it shines. One of the obvious ones is event-driven programming. That's where you ingest events from one or more streams, and this incoming event, you do some computation about it, maybe do some stateful processing on it, and then perhaps trigger an external action by sending it to an active MQ broker to do something. Some people here might find that familiar. Another popular use case is for analytics. You're processing a real-time event stream, and you're continuously updating the results as the events are consumed, and perhaps you're updating a key value store so that some dashboards so it could be updated right away. And the last, popular use case are for ETL data pipelines, but they're continuously updated. They're not run in batch. The moment the data comes in, your ETL process consumes it. So it's not an ETL batch process, but it's a forever running ETL process. And I want to add on there, I didn't put this in there, but one thing to be aware of is when you're programming with Flink, it is horizontally scalable. You could add more nodes to support more processing. And if it's a vast amount of data, it will run faster as a result of that. And there are some customers, not customers, not my customers. There are some users, companies that use Apache Flink that are using thousands of nodes. So it can handle that scale of data if necessary. Companies like Uber is using it. I believe Netflix is using it. Lyft is using it. eBay is using it. There's lots of companies that use, like, lots of Silicon Valley companies that are using Apache Flink. People like to now say that Apache Flink is the de facto standard for stream processing. I've heard that term thrown around a lot lately. Okay. Another thing to be aware of, one of the fundamentals is that it it is run as a cluster. You have a job manager and you have many, one or many different task managers. Uh, and your program is submitted with the client, and it is submitted to the job manager, and the job manager, you know, processes the data on its task managers. I'm not going to get into the details of how all of this is working right now, but I just want you to be aware fundamentally that it is a clustered program, a distributed program. And there's two components to it. Well, three components. Your program, which is submitted, a job manager, and a task manager. Okay. So now we're going to get into, like, I think the more interesting stuff here. As I said earlier on one of the slides, it's about processing data from some source and saving it into a sink. And these are examples of your sources you could use. I think the most common and popular use case is Apache Kafka, but you could use Kinesis data streams. You could use RabbitMQ, MongoDB, ActiveMQ. You could use S3, so it could actually monitor a file directory for new files, and once there's a new file in there, pick it up and make that part of your stream. It could even be like a network connection or netty, but typically what a company does is they will park data onto Apache Kafka and then process it with Apache Flink, something like that. These are all the supported sinks that I was able to find, and there's more. There's more than this if you go through other like managed services that support Apache Flink. So you could write the data back to Kafka or write it to Cassandra, DynamoDB. You could also write it to any JDBC data source, which something we were doing at my previous company. Or write it into a file sync using different file formats like Apache Parquet. If you guys don't know what Apache Parquet is, it's a columnar data storage format that you could use frameworks like Spark or Apache Flink or Presto, to read. And they show up like tables. You could query it, and it's a lot less costly to read columnar format than it is like raw CSV, for example. All right. Another important fundamental with Apache Flink is understanding that a stream element is the lowest level abstraction for data in there. Contrast this with Apache Spark, for example. Spark uses a data frame, which is multiple elements of data, whereas this is an actual stream element, which could be a Java primitive, a Java class, a tuple, a table row, a protocol buffer, an Avro element, or it could be even JSON. And to the right of my slide are examples of what the stream element could be. It could be a tuple3, in this case, a time series, and a protocol buffer representing time series. These are just stream elements that you could process, whatever you want it to be, but and using POJOs like the time series class, the Java class, works very well for Flink. And it works very well. Okay. Now I'm going to get into a part of Apache Flink that takes a while to learn. That's the notion of time within Apache Flink. There are three different types of time. Event time, where the time is inherent within the stream element. There's processing time, which is using the wall clock of the machines. And there's ingestion time, which is a timestamp that is given to that stream element the moment it enters the Flink cluster. The default time semantic is event time, and it's highly encouraged to use that. And I'll get into that a little bit more in a moment. Actually, I'll get into that right now. The reason why event time is encouraged is because it allows you to deterministically process your data across the cluster in a meaningful way. And I'll give you an example of how that works. Now, if you're using something like Apache Kafka to read your data, when you write data to Apache Kafka, there's your data that you just wrote, and then Apache Kafka also has an internal timestamp called they call it the event time. You could set it to your own timestamp, but usually Kafka just assigns it for you. Well, when Flink reads Apache Kafka, it's actually able to read those records in order. And if you allow that timestamp to remain your actual event time for processing the data, uh, you could do all sorts of wonderful things in a distributed environment. And I'll try to explain that here a little deeper. Um, well, as I say in the first slide, in the first paragraph, event time processing allows for deterministic computations across multiple nodes and windows, um, in a way that you wouldn't be able to do if you're using wall clock based processing time. For example, let's say you have 1 year of data in Kafka, and you suddenly start up Apache Flink and you're using event time processing, and you say you want a 5-minute tumbling window. Well, when it divides that data into that 5-minute tumbling window, it's going to use the timestamps that are not on. It's not going to use the processor's time to determine 5 minutes. It's going to read the data to see what the timestamp is. Your stream record has that data, and so it's going to be able to deterministically put data into that 5-minute windows in such a manner that if you had two chained 5-minute tumbling windows, and you use the same key and everything, the same data is guaranteed to be in both operators. And that's even true if you're doing if it's a distributed system with many nodes. You can't do that with processing time because those are a different 5 minutes. And it might be off several milliseconds as well. There's no way to do that with using processing time. But if you're using the timestamps that are embedded within data, it could use that as a reference for time and deterministically perform time-based computations like windowing. It took a long time for me in the beginning, I shouldn't say a long time, but in the beginning, I didn't understand this concept when I started working with Apache Flink. And I thought processing time was the way to go, even though the documentation said event time is the better way. I just didn't get it. And eventually I did. And I was like pretty amazed. So this is a really important concept to understand. Does anybody have any questions about this? Because it might be a little abstract for the first time hearing it. No? No, okay.
Hey, Marco. Mind if I ask a question?
Sure, please.
Yeah. Could you give an example to describe this concept? I feel like that could help. Like, for example, and maybe make it concrete. Let's say, like, you have a mobile application and there are events that happen on that app, maybe some sort of click or some other thing. And there are plenty of users. There are all these events being generated. That mobile app sends that event data to your Kafka stream. If you're using event time, what happens after that? Like in terms of from the Kafka stream ingestion until it reaches your stream pipeline,
So
what does that look like?
so so this Kafka source where there's the data, um, when it reads it, it will read the timestamp that's embedded in that record. And as the data is flowing through the different operators in Apache Flink, um, it'll it'll use that timestamp to keep track of time rather than what the actual time is right now, which is like 6:30. It's going to use that timestamp instead. And if you have two 5-minute windows, a window is like a time period, for example. A tumbling window is a time period. Like if you use two 5-minute windows, it's gonna actually put the same data in both windows, because the time second in the record to determine what time it is. It's not using the actual, human time that we use. And so if you're processing like 1 year of data, for example, if there is no such thing as event time processing and it's just using wall clock time, then you might load that 1 year of data literally in a minute, right? Who knows how fast it's going to do it, but it could load it all at once, and it's gonna be like such a massive amount of data that you're gonna probably run out of memory or something like that. But if you use event time, it's actually going to process it into 5 minute chunks of data as they were written to Kafka. I hope that example helps. But I'm
Yeah,
glad you asked it. Thank you.
that definitely helped. Thank you.
All right, I'll go on to the next slides. Oops. Okay, watermarks. Another concept to understand when you're working with Apache Flink is how it keeps track of the progression of time across operators within the cluster. It uses a technique called watermarking, and usually the way it works is unless you're the watermark will be, you know, when you read data, when you read the watermark, it means that you're no longer going to read data that's older than that. The data will be newer than that subsequently, unless you allow lateness. Um, if you're working with Apache Kafka, you don't need to do that because it could read the data in order. But if you're working with other types of data sources, your data might not come in order, so you want to give it like a threshold for how late data will be. And if you're actually stepping through the code when it's running, you're going to notice that um, the watermarks are used to determine when a window ended. Um, you usually these processing semantics only matter when you're doing windowing, or when you have timers, which are all possible in Flink. But it's the watermark that triggers it, that allows it to know that we're past this moment in time. It's time to do this. Um, and if you're just like time goes like from left, if you're imagining like time progressing from left to right, um, you could kind of think of the watermark as always being to the left of the new data elements. Um, I don't think I did a good job of explaining that.
I,
It's
I
kind of
have
hard to explain. Go
I
ahead.
so let's say you're using something that doesn't necessarily send your data in order, like you said, like Kafka. Let's say you get to a watermark that says the time it is right now, and stuff is not coming in order. What happens to the data that is before the watermark that you receive? What does your system use? Does it just get ignored?
It gets ignored, but you could also extract it into a separate stream and do something with it. So it'll ignore it. Um, but you could also get what's called the side output and process that data and do something with it,
Gotcha.
if necessary.
Okay.
But yeah, it will get ignored
So,
because it's considered old.
yeah, sorry. I was kind of curious, like, what's the problem that one is trying to solve?
Well, that's a great question. I I'm not 100% sure because I didn't write Apache Flink, but I suspect that the watermarks were used to um, communicate across the cluster, um, where where I guess the program is with respect to time, because time is in order in a certain respect. Uh, Even if you have even if you allow some late data, it's still in order, right? And you might have some time critical code that is dependent on a timer or even a window where it needs to divide the data in the window or fire off that timer. The watermarks allow you to proceed. It's not just looking at the timestamp and the event time, but it's also looking at the watermarks. If you're running it across a cluster, you'll see that once the watermark exceeds some certain time, then your window will trigger. And I guess it's the technique they use to determine that. I wish I could give you a better answer.
Okay. Yeah, I think I understand. It's like some kind of like a cap, right? It's kind of like a border that once we cross that, it will trigger some, I guess, some processing.
It is used for that for certain.
Yeah.
I've actually stepped through windowing code to see it do that and to help me understand what's going on there. So yeah.
Can I chime in on that? Correct me if I'm wrong, Marco. It's been a while since I've been working with Flink, but I think there's two things that watermarks are solving. One is that you just keep track and progress of event time in the system as it progresses. And I think the other one is that it lets you handle out of order events that come in. So if let's say you passed watermark 11, and so you shouldn't be expecting any events earlier than that to arrive in the system. But if that does, because network delays or the system was down or some other problem, you can incorporate logic to handle those events that come in out of data or out of order, based on whatever needs your application is going to have.
I think everything you said is also correct. Thank you.
Yeah.
All right. Operators. This is the stuff that we actually code. An operator performs a computation or transformation upon stream elements. And Flink offers 3 different APIs for writing operators. The data stream API, which is, I think, the richest out of all of them. The SQL API, which is very succinct. And a Python API, which allows you to use both data stream and SQL API and Panda data frames. And, you know, as a stream data flows through your application, it goes from operator to operator. And I just have this little example here, like you might have a map operator, which just transforms the schema of the data. You might have a filter operator, which removes certain stream elements, and then you might have a window aggregate operator, which might do an average or something like that. Some concepts to know an operator. Now, this is not the SQL that it runs, but it's conceptually easy to understand that every operator is acting like an insert into select from clause. Like you have let's go from left to right. You have your source deserializes the data, and then you select from that source with some certain where parameters. Then you insert it into your output, and the next operator will select from operators 1's output, transform it, and insert it into its operator 2 output. And then the third operator will select from operator 2's output, transform it, and then maybe write it to a sink. It doesn't, I mean, there is some SQL that might look like this, but I'm just trying to explain that that every operator can change the schema of the data and or the type of Java object that it is. And when it goes out, it could be a different format or less data. And another thing that I like to tell people is that they're like functions applied to the data on the stream. And if you think about it, SQL itself is a functional language. Although it has a beginning and an end, in stream programming, your function you don't have a beginning and an end. The stream is always running, and you just apply your function to the data and you chain those operators together. So it's good to think of each operator as its own transformation of the data. And some people, they like to put little tables to explain which each operator in and out looks like. But this is a concept to understand when you're doing stream programming. Now, Flink comes with these different types of basic operators that are some of the fundamental ones built that are your building block for your applications, but it has more than just this. You could map, which means like basically change what it is. You could do a flat map, which is similar to map, but you could actually have more elements come out of it. So I like to say, if you have stream element A, B, well, your flat map could emit A and B separately. You could do a filter, like I did on this little drawing here. It only allows B2 in, the rest are ignored. You could key the data. Now, keying your data is a very important concept for stream programming because it allows you to, if you're not using like random partitioning, key data allows you uh, to process the data in a distributed manner as well. That's assuming you're not doing, well, yeah, it does that. Another type of operator is a reduce operator. That sort of like joins two elements together. Like in the bottom, I have A and B. Well, you reduce it to one element called A and B. These are your basic operators. Another important concept in Flink are which we call windows. And they're like little batches, you could say, and they're hard at processing infinite streams. Now, there's different types of windows. I have like 3 examples here. A tumbling window, which is usually it's dividing, let's say we're talking about time here. It's dividing data in even boxes of data, even windows of data. You could say like every 15 minutes, every 5 minutes. And the data in one window won't be in the, well, it'll be distinct from each other. You could have a sliding window where the windows are overlapping, and so some data might be shared between those windows. And then there's a session window where if it detects there's a certain gap of time in data, well, it'll give it a different window. If you have more than one stream in your job, your Flink job, you can join it. You could join it with depending on what type of window you have. When you join it with the key, well, it's kind of like SQL. And if you go to the examples, like this one up here, you have the red stream and the blue stream, right? And we're doing a tumbling window join. You're going to see like a cross product of it. And then if you go down here, like an interval join, you will see that that gray area emitting from 0 hits 0 and 1. So your join is 0, 0, and 0, 1. But if you go over to 4, its interval doesn't hit anything, so it doesn't hit the join anything. But 5, it hits 6, so your Cartesian product will have 5 and 6 in it. It was fun making these diagrams, by the way. But you could join different stream elements based on a key and your window. Now, when you're doing window processing, you have to write an operator function for it, and there are 2 types of there's 2 types of window function operators, and one of them right here on this slide is the process window function. A window function performs computations for all the elements within that common window. And when that window ends, you will see an iterable of elements in it that you get to process your data. However, you could front this window function with a reducer or an aggregator beforehand, so that the only thing that shows up into your iterable would be the aggregate or the reduced results. Also, when you're running a process window function, you could get what's called the side output, which is like splitting the stream into separate streams. Another really low level operator is called a process function. This is what the signature looks like. You have your input and the collecting your output. Because you could collect outputs at any time, you could do like a flat map operation here. However, one really interesting functionality that a process function has is timers. And it supports processing time timers and event time timers. And it allows you to do things like, every 15 minutes, based on the event time, do some operation. Like you could do interpolation with it, for example. Okay. This is where stream processing gets really powerful with Apache Flink is you get to do stateful processing, which means that when you're using a rich function or a keyed process function or a keyed process window function, either of those, you have the ability to use state. It only works when you're doing key by the way. And you might be wondering, why is it only allowed for key by? Well, if your state belongs to a key, you get to look it up and do something meaningful with it. But if there's no key, then you don't really know who the state belongs to. it doesn't belong to the whole stream because you're doing parallel programming, right? The data is going across many different nodes, and if you don't have a key, then you cannot really attribute it to any of the stream elements. So I think that's why they say you have to use key by to use state. Otherwise, you don't know what type of stream element it belongs to. A key by is just a manner of partitioning data. And as it says, a state belongs to a given key. You could have a TTL. And it can be saved in memory, the file system, or the RocksDB key value database. And these are the only type of states that are supported. Value state, which is just like one variable. A list state, which is a list of data. A reducing state, which makes the data smaller in conjunction with the reduce function. An aggregating state to do aggregation that works with an aggregate function. And a map state, which is literally like a map with a key value store. Any questions about state, by the way? It's think of it as like a cache. Like an operator can have its own cache of data to do computations. You might want to, for example, store metadata about the stream elements in there. And when the data is coming in, then enrich it with that metadata, or it tells you how to process the data. There's all sorts of interesting, whatever your imagination holds, you can do with keyed state. And this is what makes Flink a very powerful stream processing framework. It allows you to do stateful processing of your data. Okay, another very important concept with Flink is it's a fault tolerant framework, meaning that there could be errors in your distributed system. It could a node could crash. You could have an exception in your data at that moment in time, and it knows how to deal with that. It knows how to restart on its own. It knows how to restart exactly where it failed. And it does that by using what's called checkpointing. The job manager manages the checkpointing. It tells all the task managers when to save their data in a checkpoint, and it acknowledges them, and it knows that it finished and tracks them, and manages writing them. But checkpoints allow the system to recover where it failed. Checkpointing requires durable storage, like HDFS or S3. And They're implemented using what they call the synchronous checkpoint barrier algorithm. I encourage you to check it out if you really want to get deep into how Flink works. And it's inspired by the Chanley-Lamport algorithm. It's pretty interesting stuff here. Okay. Execution environments. So you could deploy it onto any machine, but you could also run it in a container like Docker or Podman. You could even run Apache Flink in your IDE and debug it. I do that all the time. You could run it in a Kubernetes operator or Kubernetes as well. And there's also these different managed services that support hosting Apache Flink applications, such as Decodable or DeltaStream or Ververica. Ververica is the company that started Apache Flink, and they've since been purchased by Alibaba. But of course, they also support it. Okay, demo. Now I'm going to get into the demo part of my application. So hopefully you guys might have downloaded it so you could follow. Okay. Okay, before we begin the demo, the first thing I'm going to do is give you a quick overview of the components of the demo. It's system design. So let me open OmniGraffle. I usually use OmniGraffle for doing my diagrams. Okay, so let's see what this is real fast. Start presentation. Okay, so at the center right here, you'll see this is where my Apache Flink cluster is deployed. I'm deploying all of this to Kubernetes using the Kubernetes operator, and the Flink job, which is my code, will 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 do two things. Well, it'll do three things basically. Its data source is this time series topic. I'm actually calling it the time series topic, and it's populated by a component that I wrote called DataGen Agent JS, which is a JavaScript application that I wrote to prove that I know how to write in JavaScript, because the company wanted to know, can you write in JavaScript? So I made this component. It generates data, time series data, populates this Kafka topic, and that's the source for this job. As if you remember earlier, I said that every Flink job has a source and a sink and zero or more operators. So it'll read that source and it'll do two things with that source. One of the things it'll do, it'll save the data into the long-term store, which is S3 but deployed to local stack. Local stack is a AWS emulator. And it's going to save it in this bucket called Understanding Apache Flink long-term store. That bucket will also be configured to have checkpoints and save points. And in addition to saving the data in Parquet format in local stack S3, it'll also save the data into another Kafka topic in line format, which will be going to an application called Telegraph, which is an ingestion utility for Influx DB. So this has one source and two sinks. The source is an S3 bucket in Parquet format, and another sink is another Kafka topic, which is going to be writing data to Influx DB via Telegraph. Additionally, I also added a Kafka UI so that we could, examine which messages are being sent. And I also have it's not in this diagram, but there's also an S3 browser, so you could see what's in S3. So this is a quick overview of my demo, at least from a system design point of view. Let me get out of this screen. Come on. Okay. So perhaps I'll go over the what is it called? I will go over the some of the code as well, and the process of, how I wrote this in Kubernetes. I want to say that I am new to Kubernetes. Before I was previously using just Docker and Docker Compose. And but in my previous company, our operations team was also using Kubernetes, and I was using Kubernetes more as a user, but not as the writer. And well, I really wanted to learn how it works, and for the longest time I put it off, and I decided to use this project as my jumping point, and I discovered a lot of its advantages. So I really like the whole concept of operators, which is it's supposed to mimic a human as what they would do operating a distributed system. And for something like Kafka or Apache Kafka or Apache Flink, well, there are several components that need to be deployed and monitored and orchestrated in a certain way. And uh, Kafka operators act like a one-step install pretty much for these complex distributed systems, and it's quite powerful, as you'll see in just a moment. Okay, so the README file has my cheat sheet. So the README is also on uh on GitHub. Let's see GitHub. And let me go to my understanding Apache Flink repository. So the cheat sheet is here. I like to use my IDE, but the cheat sheet is here just so you know. And the first thing I need to do is I need to start Minkube. So let me go to step 1 of my cheat sheet. I'm going to start Minkube. I'm starting it with approximately 12 gigabytes of RAM. I don't know if it could work on less than that. There's a lot running here. Perhaps it can, but I've tested it with 12 gigabytes of RAM, and that seems to work. It takes like less than a minute usually to start Minikube, but let's see what happens here. Starting it up. Let's see what's here in the actual deployments. So the deployments that I wrote are in the conf file. And the first deployment, well, actually I need to build everything too, right? Let me open up a new window. So it'll be a fresh clean of this project. That way I could go through all the steps. So we're waiting for Minkube to start. Bear with me. All right, Minkube is started. Good. So the next step in my cheat sheet is create the dashboard, right? So let's do that here. So Minikube comes with a dashboard, and as you see, it's going to localhost, the loopback IP address. And this gives you insight as to what's going on to Kubernetes. Back to my cheat sheet. So I depend on, as I said earlier, the data gen agent. So I'm going to build that and clone that in this other window here. Cloned it. And the next step is to build the image. And I'm using Minkube to build the image. Okay, that was built. The next thing is I'm going to build my understanding of Apache Flink application. That's that's all the stuff in here. I'm building that. That's built. And the last thing I'm going to do is to build my merged version of the Apache Flink image, but with Hadoop code in it. So let me build that real fast, and I'll give you a quick overview of that Docker file because it's I think I'm the only one I know of that's using that technique. So let me show you real fast. so that Docker file, it's using a multi-stage build step. And so I'm including Hadoop as one of the name stages. Then I'm including the latest version of Flink. And all I do is I copy from the Hadoop stage into the directory opt Hadoop to the to where the Hadoop home is basically. I'm copying from Hadoop to Hadoop, and I'm deleting the SLF4j reload 4j file because SLF4j only works with only one I guess implementation, and so we don't need this one. It's going to get in the way of the class path. You don't need Hadoop for Apache Flink, but if you're going to use Parquet, you do. So when you're using Hadoop, it's recommended to just use well, I mean, I recommend to use just use the Hadoop class path. To me, that's a lot easier than figuring out all the dependencies. Maybe that's a bit extreme, but that's how I do it. Okay, back to the cheat sheet. Okay, so when you run Kubernetes, you have the ability to create namespaces. That way you could isolate your application. It's considered a best practice, so I'm going to create a namespace for my application. I'm going to call that namespace Understanding Apache Flink. Now the next step is I'm going to install the cert manager because the Flink operator relies on it. You see, it's that easy with since these are operators, all you need to do is do an install like that, and all of these components are installed, which is beautiful. The Flink operator uses Helm, so you have to install Helm beforehand, just like Minikube. So let me add the Flink operator to the Helm repo. I just added it. And then let me install it now that I've added it to the repo. And let me see if that did anything in Kubernetes. Let me go to my namespace, Understanding Apache Flink. And as you see, it does have a deployment for the Kubernetes operator, and a pod for it as well. Okay, back to the cheat sheet. And then I'm going to install the Apache Kafka Operator by Strimzi. This is it's fantastic because it allows you to deploy Kafka with Zookeeper and 3 brokers, or however many brokers you want. It's a very thorough operator. Let's go to its website real fast since I rely on it. Strimzi. Kafka on Kubernetes in a few minutes, and that's quite accurate. This is a really nice operator. So, okay, so wait, I already ran that, right? I installed the. No, I didn't install the Strimzi operator. Let me do that. Copy. Okay, so I added the Strimzi operator. Now I should add this to my instructions, but I highly recommend opening a tunnel because actually, let me go over the deployment first real fast. So these are other components that I installed that have their own I just installed operators basically under a namespace. The cert manager operator, the Kubernetes, the Flink Kubernetes operator, and the Strimzi Apache Kafka operator. Now, let me give you a quick overview of my deployment. My Kubernetes deployment before I deploy it. Actually, maybe I'll deploy it now, but I'll deploy it and I'll do the overview of it. That way it has a chance to start. So as I said earlier, you should do a tunnel in a new window. Oops, I didn't do that. Let me go to my README. Okay, there's a tunnel. And the reason why my code requires a tunnel is because and you have to put the password here. That's kind of it needs like sudo access, I guess. The reason why I need the tunnel is because in my Kafka operator, I'm exposing some ports outside of Kafka, and you need the tunnel. For some reason the Kafka operator won't start. I mean, the Kafka deployment won't work unless I have the tunnel running because of those ports, and I'll show you which ports I'm referring to. So let's go over the deployment so you have an understanding of what that is. So this first deployment in the YAML file is concerning Apache Kafka, and I have 3 listeners. The standard port 9092. I declared it internal, not TLS. Some TLS ports, if you want to use SSL on ports 9093. And then additional ports on 9094 for the load balancer. And those are the ones that are external, actually. And that's why I gave it the name external load balancer. And this one, it doesn't start unless I have the tunnels. Maybe that's not a right explanation of what's going on because I don't know fully exactly how Strimzi work, but this configuration worked for me. As I said here, I could configure the number of replicas in my Kafka cluster. So that will have 3 brokers. Some config for it. 1 zookeeper. I could add more than 1 zookeeper. Another part of my deployment is Kafka UI. It's a really nice UI for Apache Kafka, and configure it to read off the Bootstrap servers that are exposed by this Kafka cluster, which is understanding Apache Flink at port 9902. This is actually going off of a load balancer. That's why you don't need three brokers, and that load balancer goes across 3 brokers. And it's, I guess, an internal load balancer, not an external one. This is a deployment for my data gen agent. Again, it's using that Kafka cluster as one of the brokers. And when you use Kubernetes, you could write the contents of a file in a config map and then map that file to the file system, which is pretty nice. So here I wrote an init script, which makes a bucket called S3 understanding Apache Flink. That's a script. And I'm calling it init. That's what this whole like config map does. And then below in local stack, as you notice, I gave this name local stack config map. Over here, I mount a volume called local stack init, and that volume is I guess assigned this config map, which will put that file that defined there, and then that's how local stack runs that script. That's pretty cool, right? So I'm telling local stack only to use S3 as its only exposed S3 service, because local stack supports many different services. Just a quick overview of local stack. Let's see. Local stack GitHub. Let's see what's there. So this is the URL for local stack, and it's a really nice S3 emulator. I've been using it for several years now. Then I made a persistent volume for my jar file, which is the Flink deployment code that I wrote. This is the volume that it's saved in. Now this is a interesting thing that I needed for my job to run. I needed to put my jar file somewhere on the cluster, the Flink cluster, so that it could be loaded, right? Off of a volume. So I had to create the volume in there, and then my image for my code, which is this Docker file, all it's really doing is this Docker file, all it does is create a jar file. It doesn't actually run anything. So as you see, I'm in, it's a multi-stage build, so I have a, wait, is it? Well, I set it up as a multi-stage build, but it doesn't actually require that. I'm using the Gradle image, and I'm just adding my source code, which is the source main directory and the build Gradle. And then I'm building the shaded jar with the shadow jar command that's in my build script over here. So I make the jar file, and and uh and back to my deployment here. All this does is this is a batch job. See where it says API version batch? So this is a Kubernetes batch job. It's only going to run one time, and all it's really doing is copying. It's running this command right here, which copies the jar file that was built in that Docker file that I just showed you a second ago, and it copies it to the directory /deployments. And that deployments directory is going to be mounted by the Flink operator so that it runs. Here I configured Influx DB with Influx DB so that it'll run in Kubernetes. This is a single node deployment, and I think the open source version of Influx DB currently only supports single node deployments. Now, don't quote me on that, but that's my understanding. I could be wrong about that. I have a config map for the Telegraph configuration. Telegraph is a utility for ingesting data into InfluxDB. And here's the deployment for Telegraph. As you see, I mounted the volume, and then I mounted that config map so that the Telegraph conf file goes in there. And last, I made a deployment for the S3 manager. Now, when deployments run in Apache Kafka, in Kubernetes, not Kafka. When you do a Kubernetes deployment, deployments are only really accessible within the Kubernetes cluster. But if you need to, the ports, the TCP IP ports, if you need to access those ports, you need to use what are called services. I'll go over those services in just a short while. Okay, so now that I explained that, let me actually do the deployment. So I'll go to my cheat sheet. I created the tunnel already. And I will do the first deployment here. Now I separate the dependencies that are needed before I actually run the Flink operator. Okay, so I'm running that, and if you go back to the dashboard, you'll see a bunch of components were just deployed. InfluxDB, S3 Manager, Telegraph, my DataGen agent, Kafka UI, local stack. Telegraph just failed. But remember, Kubernetes is what is it called? A declarative framework. You tell it the state that you want it to be in, and then it'll resolve itself till it reaches that state. Now I kind of did a really naive deployment for Telegraph. It's not waiting for Kafka to be up yet, so it probably couldn't connect to anything. So, I mean, I could go same thing for DataGen agent. I could click on that and actually go back to the pods. And I could look at the logs and it'll tell me why it failed. And actually, I don't know if it failed. It doesn't look like it failed actually. Oh, we could go next. No, I think it just didn't start up yet. It might already be working now. Everything's green, so that means it's all good. Yeah. All right. So let's go back. So let's go over the services next. The services just open up the ports. So like I'm opening port 32180 locally. That's the node port for the Kafka UI. For local stack 32566. So if I need to do things locally from my IDE, those are the ports that I would connect to. And before I can connect to them, I actually need to make a tunnel as well. Influx DB, I try to use the 3200 range for my ports, the local ports for development. But internally, they're using just the port. They don't need to use the node port. And I'm not really sure what target port is. I forget right now. But yeah, the services are just explaining which ports from your pods that you're exposing. And as I said, all of these are running just fine right now, but I don't have a Flink application deployed yet. So that's under the Flink operator. So let me start it up first. Actually, no, I'll give an overview of the conf file. So this is using the API version right here. That means it's using the this represents the Flink operator configuration. And this documentation is all on the Flink website. So Flink Apache.org, and then you go to the Kubernetes operator. I'm using version 1.8, which is the latest. And if you go to custom resources, you'll see information about the top pod template. I'm basically following these instructions and the reference for it. Where is that? Yeah, the reference for how to make the full spec. But I'll try to explain what's going on here. The Flink configuration, this is defining what goes in the Flink-conf YAML file, which is part of a Flink deployment. I'm enabling the REST flame graph. I'm telling it to use a local stack as its endpoint and to use path style access. I'm giving it the access key and secret key. I'm not using secrets here, but that's should be possible to do that. In this section, line 39, I configured the log configuration for so that the stuff that I wrote gets logged. The pod template defines oh wait, what's the difference here? I'm kind of confused. The pod template defines how I guess certain configuration parameters that are going to be used by both the job manager and task managers. So I'm only really setting up I'm setting up two things in here. The volumes and the environmental variables that are used by it. And I'm mounting the volume. So all of them, task manager and although only job manager needs the volume for this. Task managers will have access to it too, and they will all have the same environmental variables. I'm giving the job manager like 2 gigs and same for task manager. And then this last entry defines the job, which as you see, it's under local file system deployments in that jar file that I mentioned earlier. And I'm configuring the entry point, which is my Java class, and the command line arguments for my Java class. And if you remember earlier in my slides, let me go to that slide. Yeah, in this slide, so I just showed you there's a configuration for the task managers, the job managers, and then the Flink program, right? This section right here is a Flink program. They call that a job. So job manager, task manager, and the job. That's this diagram here. And the code that I wrote is the entry point for that. And I gave the command line parameters. I'll give you an overview of the code as well a little later. Okay, so now that I've given you an overview of the Flink operator YAML file that I wrote, I will deploy it. Go back to my cheat sheet. Oh, I didn't do the services yet, right? Yeah, the deployment. So let me do the services next. I created the services. And last, I will do the Flink operator. So I deployed the Flink operator. Now I'm going to open up another window on I'm going to create a tunnel to the Flink dashboard so that I could access it locally. I'll do that over here. So there's my tunnel. Let me open it up real fast. Let me click on running jobs. Huh, there's no job running. That's interesting. When is it gonna? Why isn't my job running? Um, that worries me. I should have a job running somewhere. Um, did I do it too soon? Let me close that. Close that. Come back to the dashboard. Oh, there it is. Oh, it's been running for 21 seconds. Let me click on that. So it's creating my job right now. And this is the Flink dashboard. It comes with Apache Flink. And it gives you a job graph. So we'll go over into this in a second, but so when it's red like that, it means that it has back pressure. That's a common symptom when a job first starts. And things are becoming normal now. And you'll see that all the, you know, the the what is it called? The operators are receiving data, how many records received, right? And this is the source, and here's the last at the very tail end of the job graph are the sinks. This is the Parquet sink, and this is the Telegraph sink that goes to Apache Kafka. So let's go over the code real fast. Under source main. So my entry point is understanding Apache Flink. And the first thing I do, it's a main application, right? The first thing I do is I use Flink's param tool to parse the command line arguments. And I made my own class called parameters, which encapsulates it. And I did that so that I could just go to my parameters class and see what the command line arguments were in one nice spot. So it's easy to read. I make final variables for all the fields, and I read the parameter and its default values. And then I initialize the stream execution environment in this method that I wrote here. And this is all standard Flink code. This part is a little different. There is a non-modifiable collection and it wasn't serializing correctly, so I had to add a Cryo serializer for it. Cryo is the framework for serializing. It's a default framework in Apache Flink for serializing plain ordinary Java objects, POJOs. And then I put my parameters in the global params. That way, when the job is running, I could check the configuration and see what the parameters were for an application. If you don't do that, the user configuration will be blank. So this is the best practice that I've adopted right here, line 47. Okay. So I have a stream execution environment, and then I wrote a class called sources, which encapsulates configuring all the sources. And there's only one source in this application. So let's go over this source class real fast. So I have a source called time series source, which has to read from the parameters, the Kafka bootstrap servers, the Kafka group ID, and the Kafka topic. And also once I retrieve those command line parameters, I initialize the Kafka source using Flink's Kafka source builder. And I'm storing the data in a class called raw time series. So this is the type of the raw time series, and it's in there, the data that's in there. So the Kafka builder, you give it the bootstrap servers, the Kafka topic, the group ID. I'm telling it to start from the earliest offset, but it probably makes more sense to use like a different strategy and see what else is available here. It probably makes more sense. Okay, earliest. What other parameters are here? Oh, committed offsets. Oh, I don't want to go over this right now, sorry. But I'll just say that, and I don't know if this is doing that, but it's recommended to actually use the group ID and then a fallback plan to do if that group ID doesn't exist. I'm not sure if this does this right now. Actually, let me check if it does. What my options are. Starting offsets. What are the parameters here? Offset strategy. So yes, well, committed offsets, right? Which I don't know if it's doing that. Sorry. I wish I could tell you right now, but in the interest of time, I'm going to proceed with the presentation. I'm not sure if I'm going off the group ID, but that's what it should be doing. If it is only going off the earliest offset, then that means it's going to read the whole Kafka topic each time, which is not ideal. It's an easy fix, but I don't want to fix it on the fly at the moment. When you are dealing with Kafka, you have to make a serializer for your data. So I wrote a CSV deserializer, which turns it into the raw time series. So let's go over that real fast. You override the serialize method. I override the second version of the serialize method. That way I could collect many rather than just one. I read the headers because they're important for my code. I get the Kafka record, its payload, which is value here, and I turn it into a string. I extract the event time from the Kafka record. I make that part of my data even though I don't need it just yet. And then I use a string reader because the Apache common CSV, the CSV commons from Apache, I use that to read the CSV data, and that library supports reading multiple lines of CSV. So I read the records of CSV and I iterate over them in this loop. And when I have a valid CSV, I collect it. That's what my deserializer does. So one Kafka record could have multiple records. So that's what my source does. Oh, yeah, here's where I'm actually reading the source. So I encapsulate the source of operators and the sinks with a class that I called source operators and sinks. And the next operator I wrote called the event time operator. I might not even need it. So let me see what it does real fast. It sets the event time. That's ridiculous. It's setting the event time from Kafka, which I already did in the serializer, so I actually didn't need to do this. This is the waste of an operator. A waste of computing resources. I should probably delete this operator because the data is already there. I think the reason why I did this, I guess my brain just like I've been busy, so I made a mistake. So this operator is actually not necessary. My apologies, because my if you remember earlier, my deserializer is getting the event time here, right? And then it's assigning it that value, and so then my my event time operator is doing the same thing, which is it's assigning it twice. But you know what? They're going to be the same record actually. Um, the same data because that event time is actually part of a different. It's actually already embedded within internally with Flink. It doesn't need to read it from my Pojo. Um, okay. And it's still time series, right? The next thing I did was write what I call the type operator. It's my own thing. And the type operator, what it's doing is it's inspecting the code and determining whether the value of the time series is a string, a double or integer, whether it's numeric or string. That's what the type operator is doing. And then this one time series, I use it twice. So in a sense, I'm making two different streams out of it. Um, uh, One of them is I'm filtering using a filter so that only numeric strings go in this stream. And then I'm filtering it again so that only string time series goes in here. So let's see what those filters look like real fast. So you see it checks the type to see if it's numeric, and if it is, then it keeps it. Otherwise, the rest are filtered out. The string filter is very similar. Checks if it's a string. These are really simple functions, right? So I have two streams now. And the numeric one I'm sending to the average operator, which is a window operator, and the last operator is also a window operator. So there are two window operators here. Let's see how those work. So window of 1 minute, window of 1 minute. I'm using an aggregator and the aggregate time series operator, and I'm using a reducer and again the aggregate time series operator. So they're going to the same operator. One of them is being reduced, the other one is being averaged. Actually, these are different instances of operator. I'm just using the same code because this code is all it's doing is why is it doing that? Oh, well, it's doing two things. It's setting the event time element because it's been aggregated. It's changing it to the end of the window. You don't need to do that. This is just something I decided to do. And it's setting the step to the event time because it's now a 1 minute average. So because the data's been averaged, it's changing the time because it's gonna belong to the window now instead. So when you're in a window, in this situation, there's only going to be one value in the iterator here, the iterable, because I'm using a window and I'm using the aggregator and the reducer. If you don't front the window operator with a reducer aggregator, all of the elements in that window will show up in this process window function. But it is recommended. It's going to perform better if you add a reducer and averager. So let me show you what the averager looks like real fast. You implement an aggregate function and you're supposed to give it an accumulator, which is an object in memory that's going to you know cache the sums of your data. A method to do an add when you aggregate something. A method to merge two different objects. And finally, something to get the result, the final result that goes into the window process function. My last reducer, which is over here, is just checking which one is newer with respect to time. So if one step is after, then it changes the it uses with respect to time like the last timestamp to come in. That's how my reducer works here. So now I have two streams. This one has the averages, this one has the last value. And finally I union them like SQL. You think of these as two tables. Well, now they're not, you're unionized, but they're part of a stream. They're not tables. Then I convert them into line format with my line operator. This is just I coded into Influx. Influx encoder is my own code. But it just turns it into line format in Influx DB. And then so now I have a line operator. I aggregate those lines so that there's more than one line in the string with this aggregate function. So I'm giving it I'm telling it like if there's 1,024 records, just trigger right there. But collect it for a minute and and um and then collect it for a minute or whatever comes first, 1,024 records or a minute. After a minute goes by, then it'll collect whatever lines are there. And again, I'm using a window operator, and I have this collect lines aggregate, which is basically adding lines to each other with new lines. And finally, I route the raw time series, which is all the way up here, the original one. I route it to the long-term store, untainted, and then I route the influx collected line series line collected lines into the speed layer, which is going to be telegraphing the situation, and then I execute the job. So that's an overview of the code. You'll see now that it's been running. My job has been running for 16 minutes. Reading up here, it's collected. It's not that fast of a stream, but it's collected roughly 2,000 records. And I'll show you what those records look like. Let me open up another it's called another proxy to Kafka UI. So Kafka UI, and up another proxy, and then this is using port. Oops, maybe I did that too soon. No, I got it. So let me open up a port on localhost. Okay, so here's the UI to to Apache Kafka. And if I click on topics, I will see my 2 topics. I will see if I click on brokers, I will see the 3 different brokers that are configured. And you can even have insight to the consumers. So let's go to the topics, right? This is what the time series data looks like. If I click on topics, time series, and then messages, you will see a whole bunch of messages, and each message has multiple time series in it, headers as well, the control stream type and the content type. Let's see. Additionally, if you want to, you could go up here and produce a message, but I'm not going to do that here because the job is already running. But this tool, UI for Apache Kafka, is very handy for troubleshooting your sources and sinks if they happen to be Kafka. Additionally, the Telegraph sync is the Telegraph sync has been receiving messages as well. Influx DB line messages look like this. These are just one line. There's a special format for Influx DB called line format. Encourage you to take a look at that later. Also, let's see, sorry, moving this over. Let's go to the dashboard now for Apache Flink. So the dashboard, besides just showing your job graph, it also has other information that you might find useful. If there are any exceptions, and this exception happened when the job started up, you will see that, and the history of the exceptions. Oh, there's been quite a bit actually. But they were all at startup because they couldn't find the Kafka topic immediately. Remember, Kubernetes is a declarative framework, and it attempts to put the system in the state that you want it to be in, but it could be asynchronous in nature, and certain services might start before others. And apparently, this job started before Kafka was up and running, so that's why it was you have those errors there. You also have the checkpoints in here. You get to see the latest checkpoints, the history of them. I think this goes as far back as 10. And what else is there? There's also the flame graph, which I don't see here. When you're running Flink, you could look at flame graphs and see how it's performing. But I don't see them available here. Oh, you can get a thread dump to like see why it's stuck. That could be handy. I enabled the flame graph. I don't know why I don't see it. Maybe if you click on an operator. Oh yeah, flame graph. It's enabled in here, so I'm waiting for it to do a sample. And I guess this one is not that informative, right? Let's go to a more informative operator, one that has more going on, and the average one. Okay. Actually, not average. Let's go to the one that's always receiving time series, right? The flame graph is there. Actually, I have kind of a slow stream, so I don't expect much to be going on there. But knowing what the watermarks are, that could be, well, I don't know why I don't see the watermarks. That could be they're produced after this operator. That could be very useful to see where you are with respect to the data in Kafka. I like to go to subtasks to see which task managers are receiving any data. And there's metrics here as well. So like usually I like the number of records in. But it goes for each task manager, so you would have to make a metric for each task manager to see them both. So this is the first one, right? So if I added another one, number of records in task manager 1. Where is let me just write number of records in. Yeah, so that's the task manager number 1 and 2. So as you see there is what is the milliseconds? I thought it would be a count. Maybe I'm looking at the wrong metric. And when you look at checkpoints, you also want to see how fast they're finishing. That's pretty important. This theory tells you how long it took. So checkpoint number 12 took 660 milliseconds. Actually, that's not checkpoint number 12. I don't know which number that is. This is checkpoint number 22. And that one took 660 milliseconds to complete. Next, I'll show you the Influx DB dashboard. Let me go back to my cheat sheet. Influx DB, that's this command here. And go open up that port. So local port 8086 is now open. So let me open that up. So this is InfluxDB. The password, I didn't use secrets, although Kubernetes does support secrets. The password will be in the deployment. That's where I set the information for InfluxDB. Where is it? Init password. So the password is understanding Apache Flink. With spaces in it, right? So the username is Minmay. Password, sign in. Don't save it now. Now, you want to go to Data Explorer to see where your buckets are. So here's my tags. And let's select a name. Is there a way to select all? I don't know if there is a way to select all. We'll select the tag value. And then let's open the script editor. Because we don't want an aggregate window. We don't want the mean. We just want the data. So now I'm gonna say, and sometimes you have to adjust like for how long. I'll put 12 hours. Submit, and I do see a graph. Not much, kind of a useless chart there. Let's do maybe a table. So you get a table of the data, or scatter chart. All my scatters over here. I don't like the way it's zoomed in. Oops, maybe I should have done that. Heat map. Well, it has a variety of charts, but basically this is the dashboard for InfluxDB, and it allows you to do ad hoc queries on it for analytics, or whatever you need. Okay, another component that I have here is the S3 browser. So back to my cheat sheet. Where's S3 browser? S3 manager, sorry, that's what I meant. 32280. Okay, 33280 is open. So let me open that real fast. Oops. Local host. So there's my S3 manager, and you'll see the bucket understanding Apache Flink. has checkpoints saved in it. Checkpoint 26. The Parquet data, you can see the directory structure and the files in there. I'm not going to open the files because since this is Parquet data, you need like a special system to read it. So something like Apache Flink or Spark or Hive can read them. I noticed that there's no save points here, right? So I'll show you how to generate a save point. If you go to Apache Flink, they have this the operator. If you go to the job and you add this nonce for triggering a save point, you just go to the YAML for your operator, go to the job, and I'll just put it here underneath the job. I'll say 1. The number doesn't mean anything, you just have to change it. And then if you go back to your oh god. Sorry. There. Wait, what happened? If you go So if you apply the changes, it'll pick up that it was changed, right? So now it's running a save point. And if you go back to the S3 manager, you'll see that there's a save point there now. And this is what was saved. And if you go to the dashboard, you will also see, if you go to the checkpoints tab overview, come on. There should be, I think there should be information about the save point. There's a checkpoint, history, summary, configuration, overview, checkpoints. I thought there was right here, latest save point. Gives you information about the latest save point. And so if this were to fail, you could start it off from this save point, or if there's a checkpoint afterwards, it'll restart from that checkpoint, whatever is newer. If Flink is able to recover on its own, it will do that. But sometimes you have to start it from a cold start from an existing checkpoint or save point. What else is there here? The last thing that is on my agenda is if you are using, if you're going to connect to Kafka locally from outside the cluster, like let's say from IDE or something, you need to get its IP address. So in my cheat sheet, I do have this script that'll generate that IP address. That's right here. There might be easier ones. There might be better scripts out there on the internet, but this is the one that I found that works. So you run that command, and then locally, if I were to connect with a Kafka client, it would be that IP address. I might be able to show that with my IDE, actually. No, that's all right. And really, that's it. You know, I demoed the app. I showed you the job running. I showed you the dashboard, the Telegraph dashboard, the Flink dashboard, the Influx DB dashboard, the S3 manager. And this is all running in Kubernetes. This is my Flink job. And that's all I have to say. So if there's any questions, please let me know. And I want to thank everybody for showing up. I deeply appreciate that. And if you have any questions, you could contact me. You could contact me at mvillalobos@kinetic.com. probably can't read that, so let me make that bigger. Yeah, that's my email address. You could contact me there. You could also find me on the Slack channel. I'm often there, under my name, Marco Villalobos. And again, I want to thank you for making time to attend this presentation. I deeply appreciate that. I hope you learned a lot. An introduction to Flink and you got to see Kubernetes in action. Again, thank you. I'm going to end this meeting now. And well, bye.